Thank you. Good morning or good afternoon, evening, everybody. So we are on different time zones. So thank you, Holly, for this kind invitation, and thank you all for attending this talk. As you were saying before, I'm going to talk about a computational framework to predict failure and performance of bioinspired materials. So basically, in my research in the past years, the main focus of the research was on the design of advanced engineering materials, and in particular for structural materials. So for this kind of materials, one of the typical issues that we have in material design is this one, the strength-toughness dichotomy. So strength and toughness are basically the crucial characteristic that we are aiming for structural materials. However, most of the times these two characteristics are mutually exclusive. So what happens is that when we work with monolithic structural materials, either we work with metals, which are characterized by high toughness but a limited strength, or we can work with ceramics materials, which are characterized by high strength, but they are inherently brittle. So what happens is that most of the times, especially if we are aiming for a lightweight structure, what we do is to combine different materials and to work with composite materials. However, what happens with composite materials is that you try to combine different building blocks, but then what you get is an optimal, a good trade-off in terms of mechanical properties, but you don't get an amplification in the mechanical properties, which is what we are aiming for. And which is also what we are trying to do by finding solution in nature. Actually, nature, in this sense, provides optimal guidelines, because what we can find are a plethora of materials which have been optimized for billions of years, and they are there. So we can basically copy this material, not merely copying it, but we can take inspiration from nature to design new structural materials, which are made of pure meager building blocks, but they provide an optimal combination of strength and toughness, and an amplification of these properties about 5 orders of magnitude. So something that we cannot really achieve, not yet, at least, in our man-made materials. And if we look for biomimetic models, probably the best biomimetic models are nacre and bone. So in my research, so since my postdoc and also afterwards when I became assistant professor now at the University of Genoa as well, as associate professor, together with my colleagues, what we are trying to do is to design materials inspired by nature, and in particular inspired by bone. So bone until now has been my main source of inspiration because it is a lightweight, strong, and tough material. I don't know how much you are familiar with bone, but basically bone is an amazing structure. It's a multi-scale structure. So we have, let's say, up to 7 levels of hierarchy. So here you can have a simplified version. We are used to know the typical dog bone shape at macro to mesoscale, where we can recognize the stiff tissue and the soft tissue. So the stiff or compact tissue, also known as cortical bone, and then the soft one, also known as trabecular bone. So it's a porous tissue. But then if we take a microscope and we look at this structure more in detail, we can find at micro scale, we can find a structure which is especially if we observe the compact tissue, we can find an organized structure which is called a version structure. Well, this structure is made by a particular feature which is called ostion, so a circular repeating feature embedded into a matrix. And if we go down one level, we can find that within each ostion and in between the ostion, we can find different lamellae. So these circumferential or interstitial lamellae, which are different layers, so similar to fiber reinforced composite, where you can find different fibers And again, these fibers have different orientation, but also a hierarchical organization, where in the end, we can distinguish the main building blocks, which are collagen and hydroxyapatite. So hydroxyapatite is a mineral crystal, which is usually brittle, although here it is not properly brittle thanks to additional mechanisms which occur at nanoscale, and then collagen protein, which confers then the ability of dissipating energy under mechanical deformation. So in most of the research, we focus on the microscale structure, and we simplify this structure by considering two main building blocks. So we simplify the structure as different circular or elliptical features embedded into a matrix. So today I'm going to focus on the simplified version that we try to mimic and implement by 3D printing, and then by computational modeling as well. So basically, in these previous studies, together with colleagues at MIT and at Polytechnico, what we did was to use 3D printing as proof of concept to basically prove the validity of this bone-inspired design in order to achieve damage tolerance. So we considered this structure of cortical bone, and we simplified it into this two material structure, let's say. So we consider the material, the pure material of the 3D printer as building blocks. We keep the osteon volume fraction constant, and we combine them together in order to achieve different structures. So simplifying the osteon as perfectly circular or elliptical. And with this simple representation, which of course neglected many aspects such as the hierarchy or the interface, with this simple representation, we were actually able to at least mimic the main toughening mechanism that we can observe in real bone, and to achieve an amplification in toughness about 1 order of magnitude. But then we realized that, okay, with the 3D printer, we can leverage the versatility of the 3D printing, and we can basically design and test all the geometries that we want. But we also wanted to have a numerical framework, which is usually used in the design phase to use a biomimetic but also materials by design approach in order to reach our target properties. So we decided to work on two different fields, both on finite element models and lattice spring models. So today I'm going to focus more on the lattice spring model, as it is the main topic of this workshop. But just to give you an idea, well, the difference with finite element models is, of course, that both techniques are good, but of course, each one has pros and cons. So finite element models generally require pre-processed mesh generation and mesh refinement in the area of interest, whereas lattice spring model give the advantage that they do not require mesh regeneration, so mesh refinement. And they also provide insights into the material behavior, which was our main goal at the beginning, because we wanted to see better the toughening mechanisms that occur in these materials, since most of the times the behavior of these materials is really structure driven, so topology driven. Of course, we know that this kind of simulation are more time demanding with respect to finite element, but we still try to use both approaches depending on what we are looking at. So as a first attempt, we try to, in our first framework, we use a 2D lattice spring model where we consider a harmonic bond potential to simulate the force field. So the method is...
A question. I think you mentioned disadvantages of finite element method, but what are the advantages?
Probably I skip it. So usually they are cost effective, they are reliable because they also provide you exact information. So if you want to have an idea of the exact properties, probably final elements are more accurate in this sense. But then if we want to get they do not provide information about the toughening mechanism. So that's why we try to work on both, considering the computational time of both techniques and considering also the pros and cons of each one. What I didn't mention is also that besides finite element, we also use the extended finite element method, which allows us to see at least the crack propagation mechanism. And it's not that it doesn't need a mesh refinement. It claimed to be a mesh independent mechanism, although it's not properly mesh independent. So you need to be careful also when you use this mechanism, when you use that approach. But we try, I think that each one has its own pros and cons, but if we want to have a comprehensive view of the materials design, probably you should use both.
Thank you.
You're welcome. So coming back to this lattice spring model, we implemented a 2D lattice spring model where we modeled the crack as a zero stiffness spring, and then we modeled the interaction of the beds through springs with a force field described by a harmonic potential. So basically, of course, it's a simplified representation where we have only the elastic part, so we don't have plasticity in this model, but it's something that, of course, could be implemented afterwards. And we use all the simulation are run by using LAMS, so molecular dynamics simulation code, and we use a quasi-static loading approach, which means that we consider the two area, and we systematically apply this strain at the ends, followed by long minimization, which allows us to have a good homogeneous redistribution of stresses without affecting the edges, so without having this stress concentration at the clamps, at the edges, lateral edges. First we did a calibration based on the experimental properties, and in particular on the building blocks. So we have stiff base materials and soft base materials. But what is important is that we also have an interface, which actually plays a crucial role here. So we noticed that by modeling the interface, the behaviors change completely. So in the calibration model, we try different combination of reinforcement and metrics to find the best interface values, which could approximate the experimental curve. So why did we have to do this calibration in a systematic way? Well, because once you print, and this is very important for the printing technology, once you print this material, you actually have two materials at the beginning. So we use a polyjet technology with a straight axis printer, and basically what you have is a nozzle with different nozzle where you can, when you have the jet of these materials in more or less a liquid form, and the material are then UV cured immediately. So what happens is that during the curing, basically these materials have a really low viscosity, which means that you can have like a mixture of them. So a third material is formed at the interface. And this is proved also by the fact that in the end, we never get a failure at interface. So the material in the end are perfectly bonded due to the formation of a chemical reaction, so a chemical bond in the end, and the formation of another material. So we first did a calibration on these basic materials, and we can also see a comparison between the experimental and numerical curve. And then we implemented all the design that we previously 3D printed. So we basically have a circular ostium into soft matrix, then the reverse case, so into stiff matrix, and then the elliptical one into soft and stiff matrix. Of course, the elliptical one is very anisotropic, so was studied in both directions. So basically, all all the materials that we also 3D printed. So we could, in the end, do a validation of these models. What is interesting is that with this kind of approach, as I said before, with finite element, you can really predict the exact properties, but this was not our goal in this case. So our goal was to understand the role of the toughening mechanism on the overall behavior and try to predict which was the best topology. And in this case, we can have a great comparison in terms of experiment and simulation. And you can see how we can get the stress strain curve for homogeneous material, but also for all the topologies. And if we do a 1-1 comparison, we can see how we can mimic, of course, the stress strain curve. But what is really interesting is that we can have really get an insight into the material behavior and see how the crack propagates into each topology. So this was in a circular rostrum with soft matrix, but the same you can see if you look at the case of the stiff matrix and you see all this mechanism, or the case of the elliptical osteon, or again the case the effect of the anisotropy. So you can see here the same material tested in 2 different directions and how the crack propagates into in different ways. So summarizing here, what you can see is that with this kind of method, we can actually mimic all the bone and bioinspired composite toughening mechanism. So what we can see here is a comparison, a 1-1 comparison between the toughening mechanism that we observe in real bone. So here you can see the schematization, picture of the real bone, but also a picture taken on our experimental 3D printed specimen, and then the virtual testing, so this in silico testing. And you can see that in the end, we were able to mimic all these toughening mechanisms. So the collagen fiber bridging that here is mimicked through a polymer fiber bridging, soft polymer fiber bridging. The constrained macro cracking, which is the formation of these tiny cracks in front of the crack tip. Then the uncracked ligament bridging, again, the formation of this tiny cracks in front of the crack tip, and then the crack deflection and twisting, which is probably the mechanism which mostly contribute to the dissipation of energy and then to the toughness enhancement. So in the end, with this kind of mechanism, what we can do is to reproduce at least the strength toughness topology, which was our goal, and also we are able to predict the topology which provides a best trade-off in terms of strength, toughness, stiffness, so all the properties which we are interested into. And also to better understand the effect of the different components. So usually here, of course, we provide a simplified schematization. So we have we decided to have contrasting properties, and that was because we are kind of limited by the materials of the 3D printer. But of course, once you validate the model, then you can play with different stiffness ratio and different optimization technique and expand the design field as much as you want. Here, what we notice is the positive effect of a stiffer matrix, which really boosts the stiffness strength, the stiffness and strength combination with respect to a softer matrix. And the reason why can be provided by looking at the stress distribution. So if we analyze the stress distribution, and this is again something, another powerful thing of using simulation, if we analyze the stress distribution, what we notice is that, of course, the difference with homogeneous materials is that we have a heterogeneous stress field, which provides dissipation of the energy and different mechanism of energy dissipation, which all contributes to toughness enhancement. But what is interesting is that if you look at the stresses, so sigma x are the stress in vertical direction, so you can see the stress field plotted through this tiny line, averaged through this tiny line from the crack field to the far field. from the crack tip to the far field, what you can see is that you have a clear trend for homogeneous material with a clear stress concentration, which is typically predicted by fracture mechanics. But the difference is that within stiff and soft metrics, in both cases you have this heterogeneous stress field, but once you have a stiffer matrix, you have a reduced stress concentration. So it means that we can move through flow-tolerant material in this case, and this is better achieved if we focus instead of random distribution of circular and elliptical ocean. So after validating this numerical tool, what we did was to trying to expand the design field and try to change the topology. And in this case, this was just an initial attempt which could be further expanded by optimization studies. We combine both the circular and elliptical ocean and consider these random distributions of random orientation, keeping their the center, like the center of each one constant, so through our triangular lattice, and keeping also the ocean volume fraction constant in order to be able to compare with the previous study. And here we notice how this material actually have are reaching our flow tolerance, in the sense that if we look at stress field from the crack tip to the far field, we can notice that the peak stress is reached not only at the crack tip, but also far from the crack tip. So in this case, we are aiming for flow-tolerant materials, where the material doesn't feel the main crack anymore, but you can have different position of energy dissipation, which all can contribute to a toughness enhancement in the overall material.
Sorry, Flavia. You are saying contribute. When saying contribute, you mean contribute positively? Help?
Yeah, positive, because you get an additional dissipation. So time by time you dissipate the energy, which means that you don't get an immediate breakage. So a brittle failure as you can get in homogeneous material.
So in the sense you distribute, you try to distribute
cracks. Yeah, what happens is that the material doesn't fail by the main crack propagation. So the crack starts propagating, but then the material starts failing somewhere else. So you don't have the main big crack, which is of course energetically favored in terms of dissipating the energy. And this is important when you don't want to have this immediate brittle failure, which is something that we want to avoid, at least in structural field.
Thank you.
You're welcome. And then last year, we also tried to expand the field together with my collaborator, with the group of Professor Ryu at KAIST. So a student of this group was also expanding this study. So based on this simulation, we decided to also explore different lattices in order to design tough isotropic 2D structure composite. So again, we use computation, 3D printing, and testing. But in this case, we explore a different topology, so square, circle, hexagonal, and quasi-crystal. And the difference is that in this case, so whereas before in the previous study, we only focused on this kind of lattices, in the second study, we decided to discretize the matter based on two Breve lattices. So the triangular one and the square one, in order to better analyze the effect of loading direction. So I'm not going too much in detail on this one. So there is an additional paper if you want to take a look, and I can also provide you information. Is on composite part B, was published last year. What is interesting is that you can actually notice a difference if you have different lattice implemented. So in the if you look at all the images on the left, here we use a triangular lattice spring model, and here on the right we used a square lattice spring model with two different spring constant for the diagonal one and the horizontal or vertical one. And you can see that we have a different failure mode with respect to theoretical prediction, especially if we consider not only the two different lattices, but also the orientation of the lattices. So here is a 0 degree rotated, here is 15 degree rotated, and then 30 degrees rotated. So basically, There is also this effect that we also have to take into account, probably this one is more affected by different orientation. So in our previous work, it worked better, but we also we need to be careful and also take into account the presence of different lattices when we want to model these kind of materials. That would be useful, especially when we are working with maybe material which have like, I don't know, nanoparticles inside, or aligned nanoparticles, or some specific intrinsic anisotropy. So coming to a conclusion, trying to be on time, what we noticed is that with this kind of lattice spring model, they do not really provide an accurate prediction of the exact stress strain values, although it was not our target, as I said before. But they are able to reproduce accurately the trend of various topology, and they are a powerful method in terms of mimicking the bio-inspired composite toughening mechanism, and they also provide accurate prediction of the experimentally observed failure mode. Also, what we observed was a beneficial effect of the pattern, so in terms of stress delocalization, and a beneficial effect of a cipher matrix and random patterns in enhancing flow tolerance. So in future, as perspective, what we want to do is to better study through optimization and also machine learning random structure, and in order to reach specific properties and optimized properties, and also use a mixture of materials and not only pure materials. So in order to reduce this stiffness ratio that we had at the beginning, so find also the optimal stiffness ratio. This is on the numerical aspect. Also, what is interesting is to systematically study the effect of the interface layer, which plays a crucial role, and which is also something very important, especially in the case of bone, where we actually have this tiny border, which is called cement line. And again, also from a numerical point of view and both experimental point of view, studying random structure and maybe using also finite element model to predict the exact properties. So trying to couple different techniques. So with this, I have concluded. Thank you for your attention.